Alright, let's go. Number 10. The Twin Paradox. In 1905, a young patent clerk in Bern was not trying to break time. Albert Einstein was trying to fix a contradiction between Newton's mechanics and Maxwell's equations of electromagnetism, a technical mismatch that had bothered physicists for decades. Classical physics assumed one universal clock, ticking the same for everyone, everywhere. Forever, Einstein's special relativity said otherwise. He found that time is not shared. It depends on how fast you move through space. Take two twins. One stays on Earth. The other boards a ship and travels near the speed of light, then returns. The traveling twin is younger. Not by illusion, by fact. This isn't theoretical anymore. In 1971, physicists Joseph Hafele and Richard Keating flew cesium atomic clocks on commercial jets around the world, then compared them to a stationary clock at the U.S. Naval Observatory. The flying clocks came back off by nanoseconds, matching Einstein's predictions almost exactly. GPS satellites deal with this every single day. Their onboard clocks run faster than clocks on the ground, and engineers have to correct for it constantly, or your phone's location would drift by miles within hours. For decades, some physicists tried to argue the twin paradox was symmetric, that each twin should see the other as the one aging slower, canceling the effect out. That argument fails. The traveling twin accelerates, decelerates, and changes reference frames. The stay-at-home twin does not. The asymmetry is real, and so is the age gap. Every time you fly across a continent, you return home microseconds younger than you would have been had you stayed still. Your body has already, quietly, traveled through time. The question physicists still sit with is this. If time is not one shared river but something personal, something that bends around velocity, is there a single real you experiencing one true present moment at all? That darkness above your head tonight is not empty. It's evidence. Number 9. Olbers Paradox. In the early 1800s, German astronomer Heinrich Olbers was cataloging comets and asteroids, doing the routine bookkeeping work of observational astronomy. Along the way, he returned to an old puzzle, one that Johannes Kepler had noted back in 1610 and Edmund Halley had picked up again in the 1720s. If the universe is infinite, unchanging, and evenly filled with stars, then every single line of sight from Earth should eventually terminate on the surface of a star. The night sky should be a solid, blinding wall of light, with no dark gaps at all. It isn't. It's dark. Olbers formalized the puzzle in 1823, and for a century it resisted a clean answer. Astronomers first guessed that interstellar dust must be blocking the distant starlight. That explanation collapsed under its own logic. Dust absorbing that much radiation for that long would eventually heat up and glow just as brightly as the stars behind it. The real answer only arrived once cosmologists accepted that the universe has a finite age, roughly 13.8 billion years, and that it's expanding, stretching the light from the farthest galaxies into wavelengths we can't see, and redshifting it into obscurity. The night sky is dark because most of the universe is simply too young, and too far, for its light to have reached you yet. Every dark patch between the stars tonight is a patch of sky where light is still literally on its way. The universe had a beginning, and you can verify it just by looking up. But that leaves an older question standing untouched in the dark. What, if anything, was there to begin from? Darkness told us the universe was young. The next entry asks whether now even exists at all. Number 8. The Andromeda Paradox. In 1989, physicists Roger Penrose and Wolfgang Rindler weren't hunting for a new law of physics. They were trying to make the strangeness of special relativity easier to teach, building a simple thought experiment for students. Newtonian intuition says now is universal, one shared instant ticking across the entire universe simultaneously. Special relativity says that's false, and Penrose and Rindler made it viscerally clear. Picture two people passing each other on a sidewalk. One is walking toward Andromeda, one is walking away. Their relative velocities differ by only a few kilometers an hour. But because simultaneity itself depends on your reference frame, there are two definitions of right now on Andromeda, a galaxy too. million light-years away are offset by a meaningful stretch of time, potentially days. Two people standing meters apart disagreeing about what is currently happening in another galaxy, and both are correct. Every attempt to rescue a single, universal, agreed-upon present moment failed once relativity was confirmed experimentally, again and again. From particle accelerators to satellite timing systems, there is no cosmic clock ticking the same beat for everyone. Now is not a fact about the universe, it's a fact about you, and how you happen to be moving through it. Somewhere on a sidewalk today, two strangers just passed each other, and in that instant disagreed about the present tense of an entire galaxy. If now isn't shared between two people on a sidewalk, what happens when two particles are billions of light years apart? Number 7. The EPR Paradox. In 1935, Einstein wasn't trying to prove quantum mechanics wrong outright. Working with Boris Podolsky and Nathan Rosen at Princeton, he was trying to show the theory was incomplete, that it was missing some deeper, hidden variable that would restore a sane, local universe. Classical physics assumes objects have definite properties independent of measurement, and that nothing influences another object faster than light can travel between them. Einstein, Podolsky, and Rosen constructed a scenario using entangled particles to expose what they believed was a flaw. What they found instead unsettled physics for the rest of the century. Two particles, entangled at creation, then separated by enormous distances, remain linked. Measure the spin of one, and the other's corresponding state is determined instantly, no matter how far apart they are. Einstein called it spooky action at a distance in that 1935 Physical Review paper, and spent years trying to disprove it. In 1964, physicist John Bell, working at CERN, derived a mathematical inequality that could actually test whether hidden local variables could explain the correlation. Experiments by a line aspect in the early 1980s, and a landmark loophole-free test published in Nature in 2015 by Ronald Henson's team at Delft University, confirmed Bell's predictions and ruled out local hidden variables. The entanglement is real. Either information is moving faster than light, or space itself does not separate two entangled particles the way our intuition insists it must. Somewhere right now, a particle 1,000 light years from Earth may be correlated with one sitting in a lab down the street, and neither cares about the distance between them. If two particles can ignore distance completely, what happens to distance at the edge of a black hole? Number 6. The Black Hole Firewall Paradox. In 2012, physicists Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully at UC Santa Barbara were not trying to overturn general relativity. They were working on a narrower problem, information loss in black holes, trying to reconcile Stephen Hawking's earlier work on black hole radiation with the quantum principle that information cannot simply vanish. General relativity's equivalence principle predicts that falling through a black hole's event horizon should feel completely uneventful, no dramatic sensation marking the crossing. Quantum mechanics, applied carefully to preserve information, predicts something else entirely. A wall of high-energy radiation right at the horizon, lethal the instant you touch it. Almheri, Marolf, Polchinski, and Sully prove mathematically, in their 2012 paper, that you cannot have a smooth horizon, preserved information, and standard quantum mechanics all be true simultaneously. Something has to give. Physicists have proposed complementarity, where the contradiction is resolved by the impossibility of comparing both viewpoints at once, and holographic ideas involving wormholes connecting entangled black holes, but no consensus has formed nearly a decade and a half later. One of the two most rigorously tested frameworks in physics, general relativity or quantum mechanics, breaks down at the horizon of every black hole in the universe. Physicists still don't agree which one bends first. Even Maxwell, in the 19th century, found a way to break physics using nothing but a locked door. Number 5. Maxwell's Demon. In 1867, James Clerk Maxwell wasn't attacking thermodynamics. He was trying to build an intuitive illustration of statistical mechanics for students and colleagues. He imagined a tiny, intelligent being guarding a trapdoor between two chambers of gas, sorting fast molecules from slow ones without expending any energy, and in doing so, seemingly creating order from disorder and violating the second law of thermodynamics, the law stating that entropy in a closed system always increases. The setup predicted the demon should be able to build a temperature difference for free, extracting usable energy from nothing. For over a century, no one could cleanly explain why this shouldn't work. Physicists proposed that the act of measuring each molecule's speed must cost energy, but careful analysis showed measurement alone could, in principle, be made arbitrarily cheap. The real answer didn't arrive until 1961, when Rolf Landauer, working at IBM, showed in a paper published in the IBM Journal of Research and Development that the demon's memory is the problem. Erasing or resetting that memory to sort the next molecule has an unavoidable minimum energy cost, and that cost exactly balances the books. Physicist Charles Bennett extended the proof in 1982, closing the loophole for good. The universe survives Maxwell's demon, but only because information itself turns out to be physical, with a real thermodynamic price tag. Every memory you erase, every thought you let go of, costs the universe something measurable. If memory has a cost, what does existing at all, statistically, cost you? Number 4. The Doomsday Argument. In 1983, astrophysicist Brandon Carter wasn't trying to predict the extinction of humanity. He was exploring an idea in probability and cosmology known as the anthropic principle, questioning what it means that conditions in the universe happen to be suitable for observers like us. Along the way, he stumbled onto something darker. Standard reasoning assumes your position in a sequence tells you nothing special about the sequence's total length. But Carter, and later philosopher John Leslie in his 1996 book The End of the World, applied Bayesian probability to human population and found something uncomfortable. If you consider yourself a randomly selected human from the entire set of humans who will ever live, and roughly 117 billion people have lived so far, simple statistics suggest you're unlikely to be among the first tiny fraction of a much, much larger total. The math implies humanity is more likely closer to its end than its beginning. No asteroid required. No plague, no war, no AI catastrophe. Just population statistics. Critics have proposed several counters, arguing about reference class selection, about whether you can meaningfully treat yourself as randomly sampled at all, but none have fully dissolved the argument, and it remains debated in serious philosophy and physics journals today. If Carter and Leslie are right, then somewhere in the total span of human existence, one that could stretch for hundreds of thousands more years or end shockingly soon, you happen to be reading this uncomfortably close to the middle. Or worse, the end. Watching something can apparently stop it from happening at all. Number 3. The quantum Zeno effect. In 1990, physicists Wayne Itano, Daniel Heinzen, John Bollinger, and David Wineland at the National Institute of Standards and Technology weren't hunting for a way to freeze reality. They were studying the behavior of trapped ions under repeated measurement, refining atomic clock techniques. Standard quantum mechanics predicts an unstable system, like a radioactive atom or an excited ion, will decay at a fixed statistical rate if left alone. Itano's team found that if you measure the system frequently enough, interrupting it again and again before it has time to evolve, the decay is suppressed. Watched closely enough, it barely happens at all. Their 1990 paper, published in Physical Review A, confirmed the effect experimentally, and it was named after Zeno of Elea's ancient paradoxes of motion. Where dividing a journey into infinite steps seems to make progress impossible. Physicists initially wondered if this was a measurement artifact, a side effect of disturbing the system rather than genuine suppression. Follow-up experiments ruled that out. The freezing is real and reproducible, somewhere in a physics lab. Right now. An unstable particle is being kept artificially stable purely through the act of being watched. Observation is not passive. It is a force that reaches into a system and holds it in place. If watching something can freeze it, what does it mean that hot water can outrun cold water to the exact same finish line? Number 2. The Mpemba Effect. Aristotle noted something strange about water more than 2,000 years ago, and for most of history it was dismissed as folklore. Under the right conditions, hot water freezes faster than cold water. In 1963, a Tanzanian secondary school student named Erasto Mpemba was simply trying to make ice cream in a school cooking class. He noticed his hot mixture froze before his classmates' cooler ones, and when he asked his teacher why, he was mocked and told it was impossible, since it violates the intuitive expectation that a substance closer to freezing temperature should always freeze first. Mpemba didn't let it go. He tracked down physicist Denis Osborne at the University of Dar es Salaam, and together they published a formal paper on the effect in 1969 in the journal Physics Education, confirming the observation experimentally. Since then, physicists have proposed multiple explanations: faster evaporation reducing the hot water's volume, different rates of dissolved gas escaping. Convection currents, differences in supercooling behavior. Each explanation accounts for some experimental results and fails to account for others, and as of now, there is still no single, universally accepted mechanism. A basic property of the most common substance on Earth, something you interact with daily, remains, after 60 years of formal study, only partially understood. And the deepest mystery on this list isn't hiding in a lab, it's hiding in nothing at all. Number 1. The Vacuum Catastrophe. Quantum field theory doesn't just describe particles. It predicts that even a perfect vacuum, a region of space with absolutely nothing in it, should still contain energy, because quantum fields never fully settle to zero. Physicists were not trying to create a scandal when they calculated this number. They were doing standard bookkeeping, summing the zero-point energy of every quantum field permitted by the standard model. The predicted vacuum energy density came out enormous. Then astronomers measured the actual energy density of empty space using cosmological observations of the universe's expansion rate. Most famously through the accelerating expansion first reported in 1998 by Saul Perlmutter, Brian Schmidt, and Adam Rees's teams. The real number was almost unimaginably smaller than the prediction, off by a factor on the order of 10 to the power of 120. Cosmologist Michael Turner has called it the worst prediction in the history of physics. Physicists proposed supersymmetry to cancel out the excess, but no supersymmetric particles have ever been detected. They proposed anthropic reasoning, that we simply live in one of countless universes where the number happens to be survivable, but that explanation is unfalsifiable by design. Neither has resolved the gap. Empty space, right now around your body, should be roaring with energy according to the best tested framework in physics, and instead it is nearly, but not perfectly, silent, and nobody can explain the difference. All 10 of these sit at the center of our most trusted theories, not the edges. They are not fringe ideas or shaky data. They are the load-bearing walls of modern physics, cracking under their own weight. The universe is not confused about how it works. It has been running these rules consistently for 13.8 billion years without asking our permission. We are the confused ones, staring at equations that work perfectly and still don't make sense to us. Maybe that gap isn't a flaw in the universe at all. Maybe it's a flaw in the size of the minds trying to read it. If you want to see more videos like this, click the video on screen now.